Good morning, everybody. Sorry about that. iPod ran out of juice. Today we're starting on chapter 20. The housekeeping note, there's going to be no recitation today. So if you normally had it on Friday, we're not going to do one because the Thursday class also didn't have one. All right, we're going to start off with some nomenclature, which is fairly straightforward. The final's on Thursday, which is just exam 4. The final isn't necessarily, it's like as cumulative as everything else has been. So like your synthesis problems will use reactions from other chapters, but it's not specifically a cumulative final. All right, so we are doing carboxylic acids. You guys have probably heard the name before for these if you have a carboxylic acid at the end of your molecule. Our suffix is now going to be enoic acid. So for this here, we have 4 carbons. This would be butane. So you'd refer to this as butanoic acid. This will actually be our new highest priority in terms of naming. What do I think through this? Other is just like halogens or ethers or everything else. If we have something a little more complicated, oh yeah, I gotta add alcohol into there. I forgot alcohols. All right, so taking a look at this, we're going to start numbering based off of it always starts on our carboxylic acid. You never have to indicate where your carboxylic acid is because it's always number 1. Taking a look here, we have a hydroxy on 2. We have a chloro on 3. A methyl on 4. Taking a look at our R and S on 2 here. Oxygens are directly attached, so it's going to be R number 1. We've got a bond to chlorine, bonds to oxygen. Chlorine is a larger molecule, so chlorine should be 2. Oxygen side to be 3 here. This is going clockwise. It's going to be R. On the chlorine side, chlorine's going to be 1, carbon bond to oxygen, carbon bond to 2 carbons. Oxygen's bigger. Also going clockwise, also should be R. Putting it all together, this would be 2R, 3R. C would come first, so 3-chloro. H would become next alphabetical, 3-hydroxy. For methyl, we've got a 5-carbon chain, so pentanoic acid. So suffix, anoic, and then acid at the end. All right, so that's our nomenclature. We're going to talk a little bit about how to make carboxylic acids. For the most part, we've done this a few times already. The way that we usually do this would be to take an alcohol and throw in a strong oxidizing reagent. So we take a primary alcohol, throw in chromic acid, so Na2Cr2O7, H2SO4, and water. We can oxidize this to a carboxylic acid. A couple of other options. One of them is going to deal with nitriles. The other one is going to deal with Grignards. So if we take this alkyl bromide here, throw in NaCN. So throwing in a nitrile, going to do a very basic SN2 reaction. Kick out this bromine, make a nitrile. From this point, if we add in H3O plus and heat, and we're going to go through this mechanism a little bit later today. This is going to let us take a nitrile and change it into a carboxylic acid. So something to note is that we are extending our chain by a carbon. So this was a three carbons to it. Our final product is 3 carbons. As opposed to on the bottom here, we're starting with 3 carbons. We're ending with 4 carbons. So we've slightly extended our chain. That last carbon came from our CN. The other way we can do this is through a Grignard. So taking the same starting material with added magnesium, it'll turn this into a Grignard. And then throwing in CO2 followed by water. Our Grignard can attack a CO2. Creating a carboxylic acid, which we can protonate with the water. To get to here. Again, we're adding an extra carbon for this. So we're starting with 3 carbons. And we're ending with 4. All right, so carboxylic acids themselves are not particularly useful. They tend to be kind of bad leaving groups. They're really difficult to protonate in order to kick out water or anything like that. So what is used much more commonly is what's called an acid chloride, which has a much better leaving group. So in order to make an acid chloride, we're going to take a carboxylic acid, throw in SOCl2, this is going to replace that OH on the end with a Cl, which is going to be a much better leaving group, and it's going to give us some byproducts. So the way this works, pretty similar to what we were doing with just an alcohol. So you take SOCl2 with a carboxylic acid, our electrons from one of these oxygens is going to reform with carbonyl. We're going to attack a chlorine. Oh, sorry, attack a sulfur. We'll then kick out a chlorine. From here, We've generated a much better leaving group. So we're going to have Cl come in and attack at our carbonyl center. The electrons are going to temporarily get kicked up with this oxygen. They're to come back down to kick out this SO2 and Cl. We're running a little low on space. And then that, well, plus SO2. And then that Cl minus that we kicked out can grab this H here to give us a product. All right, kind of a long mechanism. At the end of the day, really what you care about is making Jesus Christ. Cl2 here, or sorry, this acid chloride here. Once we've made an acid chloride, they're really useful. Because they're highly reactive. This OH here was a bad leaving group. Alternatively, this chloride here is a really good leaving group. So if we take pretty much anything and add it into solution with this acid chloride, we're going to be able to derivatize our acid chloride. So let's start with making ethers. So if I take, I don't know, propanol here and a little bit of pyridine, propanol can come in, do a nucleophilic attack. On our carbonyl center. Our pyridine is going to pull off this proton. We'll kick out this chlorine here. To make an ester. And then using the same concept, we can do a whole bunch of reactions. So we could also do this with water. It's going to follow almost an identical mechanism. Well, basically an identical mechanism. We're just using water instead of an alcohol. So if we add in an amine is its own base. So we don't need pyridine as well. It's going to let us make an amide. We can also make substituted amides. Our amide mechanism is relatively the same. Going to come in, attack our carbonyl center. Another of our amide is going to come and pull off a proton. And then we'll kick out our chlorine. And then for like the secondary and the just ammonia, you just basically have less or more substituents on your nitrogen. But it follows the exact same concept. All right, so there are a few more of these. I'm not going to entirely go through how to do them. We're just going to talk through them kind of lightly. So throwing an LAH with a acid chloride. I guess we kind of do all of them. So you start with the carboxylic acid. Add an SOCO2. You can make your acid chloride to go backwards. You need to add an H2O and pyridine. We can make an ester by adding in a alcohol and pyridine. If we add an ammonia, And generally all these require excess because you need it also to act as its base. So we can do ammonia, primary amine, secondary amine. Some other ones that are generally thought of is we could add in LAH and reduce this down all the way to the alcohol. We could also add in a more hindered version of LAH. So this is going to be, so LAH is Li, Al, H4. We add an Li, Al, OR3H. It's a little bit more hindered. It's got this large group here instead of just having a bunch of hydrides. There's only one 8 hydride that can be donated. This is going to allow us to stop our reduction halfway through. At this aldehyde here. This is only going to work for a carboxylic acid. It doesn't work for an ester. Or sorry, it only works for an acid chloride. It doesn't work for a carboxylic acid or an ester. All right, if you do a Grignard on a acid chloride, it is going to add 2 equivalents of whatever you put in because it's a good leaving group. It makes a ketone immediately. We're going to be left with this alcohol. The last thing that we can add is what's called a cuprate. We are not going to spend time talking about a mechanism for these. It's similar to a Grignard, except you're able to do, it's more of like, it's our soft alkylating reagent, so it's only going to add once. It's a little more hindered. And this is going to allow us to make a ketone. And again, this is something that only works for acid chlorides. It won't work for carboxylic acids or esters. So if we add in, let's put an ethyl here. This is going to let us add an ethyl group. In order to make a ketone. All right, so this is our acid chloride. It has a lot of applications to it. You can pretty much do anything you want, as opposed to a carboxylic acid, which is just a bad leaving group, so it's not used very often. There is a different kind of similar reaction we can do to making an acid chloride, which is called making acid anhydride. We're going to talk about them briefly. I usually tell people that they are less useful because they can kind of break apart in two different directions. So if instead of adding in, or I guess if we take an acid chloride and we add it to another carboxylic acid, actually we need base first. We should do this the opposite way. So if we take a carboxylic acid, throw in NaOH, we can pull off our proton. This will do an attack on a carboxylic acid. Or sorry, an acid chloride. That kind of condense this mechanism will end up kicking out that Cl. And we can make what's referred to as an acid anhydride. These have the ability to do anything that a acid chloride could. They just tend to get a little bit messy because there's no reason why you can attack one carbonyl versus the other one. So for instance, if we took our primary amine, we could have this attack here, kick up these electrons. We'd have another equivalent of our amine pull off. A proton, oops, a little off screen. A proton here. Nope, I need that to be a single bond. This is a good leaving group, so we'd kick it out. And generate a product like an acid chloride would. The problem with this is that there's no reason why it would attack at this center and not this center here and generate your other products. because you could just as easily break apart the other carbonyl here. So that's why they tend to get used a lot less than acid chlorides. One, it takes an acid chloride to make, so it's a bit redundant. And two, its products are much more messy. But your book does go through and talk about them, and it can essentially do every reaction that acid chloride could. It's just question in the chat. So the second product wouldn't necessarily look the same. It would look the same. Let's see. It depends on what kind of acid chloride you have. If you have this and you add in, let's say, I don't know, ethanol. This is going to generate this ester and this ester here, because you have both the same thing on both sides. If we make our anhydrides different, or our two halves different, when you attack the left side, you'd get this ester, but when you attack the right side, you get this ester. So it kind of depends on what you're starting with for your acid chloride, which is why, or for your anhydride, which is why these get a little bit messy. So, okay, we're gonna take a little break. We're gonna meet back at 10:05 and talk through the rest of this chapter. So I will see you guys in about 8 minutes, where we will get back to it. All right, we're going to start on some other mechanisms. So we're going to do a little bit of what's referred to as the Fischer esterification process. And this is if for whatever reason you really don't want to use an acid chloride and you want to transform a carboxylic acid into an ester, we can add in methanol and H plus or just any alcohol. Let's use ethanol. We can go through this and generate an ester. So the way this works is we're going to pick up a proton, kind of like we would with the carbonyl. All these steps are going to be reversible. We can have our alcohol come in and attack. Alcohol can pull off. The proton, we're going to do a bit of a transfer, so pulling off the proton here. Yeah. Reinserting it onto one of these two oxygens. At this point, they're identical, doesn't matter which one. We can kick out this water. In order to create our protonated version of our final product. And then either the water we kicked out or another alcohol can come in and grab this proton. To give us an ester. This is totally reversible, so we can also do this in the exact opposite direction in order to get back to our carboxylic acid. So depending on concentration, we can either do this in the forward or the reverse direction. We add in a lot of H plus and ethanol here. We can drive this towards. That was nothing. And ester, if we instead flip it and generate a lot of H plus and water, we can drive this back towards the carboxylic acid. Esters, as we've talked about previously, are useful. We can add an LAH to them or do Grignard attacks with them. All kind of things we've seen previously. So throwing in LAH. Let's make alcohols. Throwing in Grignard, it's going to add twice. Like so. So a lot of these reactions you are able to go forward to, but not necessarily reverse to at this point. So for making an amide, the only real way we know how to make these is to start with an acid chloride. So taking your carboxylic acid, adding an SFCl2. Oh, stupid step. And then we could throw in ammonia. In order to make an amide here. From an amide, we could go back to a carboxylic acid through a similar mechanism to what we used to make an ester. So if we take this amide, throw in H3O plus, we're going to do something very similar. We're going to pick up a proton. Here, generate our protonated carbonyl. From this point, our water can come in. I'm going to draw this the quick way. So we're going to have our nitrogen just pick up this H, do a direct proton transfer. That is now a better leaving group. This can come down, kick out ammonia. Nope, not ammonia still. And then we can lose that last proton. In order to get back to our carboxylic acid here. This one is not going to work in the opposite direction. So we can use a, give it a second to get caught up on writing this. Carboxylic acid. Add an H plus, say methanol. We also go back in the other direction. H plus water here. For making an amide. It's going to require 2 steps, so SlCl2 followed by ammonia. But we're still going to be pretty much always be able to go back to our carboxylic acid just using H plus and water. Okay, from our amide, we're also able to reduce this. If you throw an LAH, this is going to reduce down to an amine. Which is nice. It gives us a way to make amines. Other than making a imine and reducing it. So up till now, the only way we really learned how to make one was to take a carbonyl, add an H plus, prime amine, make an imine, and then throw an LH. Now we can also make one through this amide pathway. Our last reaction that we are going to deal with is nitriles. So a nitrile is only really going to be available through making an amide. So taking a carboxylic acid, throwing an SOCl2, it's going to let us make an acid chloride. We could go back in the reverse direction. H2O and pyridine. our SOCl2 is going to let us make an amide. Which we could take back to a carboxylic acid with H plus and water. And then the last reaction we're going to talk about, well, not the last reaction, but the last stage of this is we're going to talk about is if you take SOCl2 again, we're going to be able to make a nitrile. Which we can do a few things with, one of which is going to be throwing in H plus and H2O, and it's going to let us go all the way back to a carboxylic acid. So something to note is that we don't have a good way to go just one step back or two steps back. Same thing with our amide. We can only go straight to our carboxylic acid. We can't go back to this acid chloride here. So we have some ability to go forward and backwards, but not complete. So all these red lines do not work. Okay, so let's start off by talking about how to do this reaction here. It seems a little odd. You can keep adding in SOCl2 and keep creating new things. Our mechanism for this one is going to be pretty straightforward. We're going to start with our amide. As well as ethanyl chloride. We're going to have our nitrogen come down, make an imine, pull off, and then our oxygen can come and attack our sulfur. Electrons from our oxygen can kick out one of these two chlorines here. That chlorine can pull off a proton from our amine. We're going to end up making a triple bond, kicking out this oxygen, and then this subsequent chlorine here. Giving us a protonated nitrile, which that last chlorine we kicked out can come in, pull off. To give us a nitrile. There are a couple of reactions we can do once we have a Grignard. The first is that a Grignard is actually, or nitrile is a pretty decent way to make a single addition to a Grignard, or to what was originally an ester or carboxylic acid. So if we take a nitrile, throw in a Grignard, we're gonna make this protonated amine, or this, sorry, negatively charged amine here, which is pretty stable on its own. It's not gonna want to take another nucleophilic attack, so it's just gonna stop here. Because if it got attacked again, it would get a negative, double negative charge, which is just not gonna happen. And then from this point, if we throw in water, we can hydrolyze this off. I guess we need H3O plus. To a ketone here. So nitriles are a pretty decent way to make single additions to what was at one point in time an ester or a carboxylic acid. Another thing we can do is if we throw an LEH, this will fully reduce this down to an amine. In a very similar manner to what it does with an amide. This yet again lets us make an amine through this kind of similar LEH pathway. All right. The last thing you can do with a nitrile is you can hydrolyze it all the way back to a carboxylic acid. This is going to be a really long mechanism. If we add an H3O plus and heat, this will initially go back to an amide. But the way we make amides into carboxylic acids is using the exact same reagents. We already have them in solution, so it's going to take it all the way to a carboxylic acid. I'm going to attempt to get this all onto one page. So taking a nitrile, throwing in H3O plus, so just H plus. Will allow us to pick up this proton. Ooh. Our water can come in and attack. Going to kick up one of the bonds of this treble bond in order to make, it kind of looks like a reverse amide. Double bonds to the nitrogen, single bonds to the oxygen. I'm going to do a quick proton transfer. So I'm going to have the nitrogen pick up this proton. We're going to make a double bond, kick this one up, and this is going to switch us to what looks like this here, which I'm just going to re-rotate around. We can have another water pickup. This H here. To give us our amide. We generated H3O plus in that last step, which is our starting material for our amide. So this is kind of our halfway point. So now we're just going through our amide pathway, which we've already done. So the amide will pick up an H plus. On its carbonyl. We can have our water come in and attack. I'm going to do the shorthand proton transfer, so we're just going to grab the proton from our water. One of our two oxygens can kick this out. Nope, that guy's gone. And then either another water or that ammonia can pick up this last proton off our oxygen to get us all the way to our carboxylic acid. So that was what? 1, 2, 3, 4, 5, 6, 7, 8, 9 steps, not including proper proton transfers where you have something else pull it off and then attack it. So quite a long mechanism. Let's do a little bit of a review. I think we're going to end a little early today. So talking about these kind of webs we can make with just carboxylic acids. Taking, I don't know, let's just say ethanoic acid. Adding in H plus. And methanol. lets us generate methyl ester here. We could go backwards with H3O plus. We could add in a LAH. This is going to let us fully reduce this down. There's another reagent I didn't really talk about much. It's called Dibol. You take an ester to it, it lets you make an aldehyde. You might see it in the homework. It's a little bit of a softer reducing agent. You could also throw in a Grignard. And this will let us generate an alcohol. We can generate an amide through an acid chloride. And then throwing in ammonia. From here, we could either go backwards with H3O plus, or we can take this to an amine by throwing in LAH. Or nitrile by throwing in SOCl2. From our nitrile, we can either go back to our carboxylic acid with yet again H3O plus and heat. We could take this to the same amine down here with LAH. Or finally, we could take this to a ketone with a Grignard. Followed by H3O plus. So this is quite a few reactions we're able to do, which for the most part don't involve SOCl2, but we're able to kind of create this big web out of them. Okay, this is all of chapter 20. So I'm going to stop here for today. As a reminder, there's no recitation today. We will do office hours at 12 still. I'll get homework 4 uploaded today, as well as getting the quizzes transferred over so you guys can get a sense of your grades up to this point. So by the end of the weekend, I want to have all the quizzes inputted into Wiley, so you guys can figure out exactly, help you guys calculate where your grade are so far. So I will see you guys on Monday. Have a great weekend.